what if I told you there's a single, simple rule that underpins all of physics? And I don't mean just some of it, I mean everything. From how a planet orbits a star all the way down to the super strange world of quantum mechanics. Okay, let's dive right in, because today we're going to explore one of the most profound and honestly one of the most powerful ideas in all of science.
I mean, just let that sink in for a second. Every single principle, every law you've ever learned, think about it. Classical mechanics, electromagnetism, even relativity, all of it could potentially be replaced by one single elegant statement. The sheer scope of that is, well, it's breathtaking. So of course, the big question is, to find the answer, we've actually got to go back in time. And we're not starting with some grand, complex theory. Nope, we're starting with a surprisingly simple puzzle, one that completely stumped the greatest minds of the 17th century.
All right, so we're talking about the problem of fastest descent, the quest for the quickest path. The setup is really simple. Imagine you've got a ball or some kind of mass at a high point, let's call it A, and you want it to slide down a ramp to a lower point, B. The question is, what shape should that ramp be to get the ball from A to B in the absolute shortest amount of time?
Now this is where things get tricky, because your first guess, your gut instinct, is probably going to be a straight line, right? I mean, it's the shortest distance between 2 points. But that's not the right answer. See, if you make the ramp curve downwards at the beginning, the ball picks up speed way earlier. And that initial burst of acceleration, it more than makes up for the fact that the path is a little bit longer. It actually gets there faster. So what is that perfect curve?
Well, people have thought about this before. Galileo took a crack at it way back in 1638 and guessed it was a piece of a circle. But he was wrong. Fast forward to 1696. A brilliant and, let's be honest, a pretty boastful mathematician named Johann Bernoulli throws down the gauntlet. He issues a formal challenge to all the best minds in the world. And who ends up taking the bait? None other than Isaac Newton himself. The story goes he was super annoyed at being bothered, got the problem after a long day working at the Royal Mint, and solved it. Overnight.
And get this, Newton sent in his solution anonymously, but his genius was just unmistakable. When Bernoulli saw the proof, he supposedly said, "I recognize the lion by his claw." He knew only a mind like Newton's, a true lion of mathematics, could have done it. But here's the crazy part. Bernoulli had his own stunningly creative solution, and his idea came from a completely different field of science.
Okay, so nature's secret here was all about least time, a clue from the behavior of light. See, the key wasn't to think about falling objects at all. No, the real secret, it was hidden in the way light travels. And this is where the story gets really clever. This all comes down to something called Fermat's principle of least time. Basically, back in the 1650s, a guy named Pierre Fermat figured out that light is, well, it's kind of lazy in a smart way. It doesn't take the shortest path, it always takes the quickest path. You've seen this. When you stick a straw in a glass of water, it looks bent, right? That's refraction. Light bends when it goes from air to water because it's trying to minimize its travel time. It changes its angle so it spends less time slogging through the slower medium, the water. And this is Bernoulli's brilliant insight. This was his genius move. He completely reframed the problem. He thought, okay, forget the sliding mass for a second. What if it's a ray of light? He imagined the light traveling through different layers, kind of like air getting thicker and thicker. As the real mass falls, it speeds up, right? Well, in his analogy, that's like light entering a new layer where it can travel faster. So he just applied Fermat's principle of least time to his light analogy, and boom, out popped the solution. So what was the solution? The answer. It wasn't a straight line. It wasn't a circle. It was something called a cycloid. And what on earth is a cycloid? It's actually a really beautiful curve. If you imagine a point on the rim of a rolling wheel and trace its path, that's a cycloid. That's the path of fastest descent. It was just this astonishing solution that connected mechanics and optics, but it was a hint at something much, much bigger.
And this leads us to the big one, the principle of least action. We're moving from least time to a truly universal rule. You see, Bernoulli had, without even knowing it, stumbled on a clue to something universal. And it begged a huge question. Why should nature only care about minimizing time? What if time is just one piece of a bigger puzzle? What if there's a more fundamental quantity that the entire universe is always trying to optimize?
Well, along came a French scientist named Maupertuis. He gave this special quantity a name. He called it action, and he defined it, at least at first, as a pretty simple thing. Mass times velocity times distance. But his claim was anything but simple. He said that for any process in nature, out of all the possible ways it could happen, it will always, always choose the one path that minimizes this thing called action. I mean, listen to how he put it. He said, this action is the true expense of nature, which she manages to make as small as possible. He literally saw it as a cosmic law of economy, that nature is fundamentally efficient, always trying to cut down on its expense. For the time, this was a truly revolutionary idea.
So you'd think this world-changing idea would be celebrated, right?
Nope, it was absolutely torn to shreds. Maupertuis was attacked by his own friend who accused him of plagiarism. He was relentlessly mocked by the famous writer Voltaire. The scientific community pretty much just ignored him. His big principle was seen as, maybe a cute philosophical idea, but it didn't have the hard math to back it up. It looks like his legacy was completely doomed. But the idea was just too good to die. It didn't disappear. Instead, it was like it got passed down through this incredible lineage of scientific giants. Over the next 100 years or so, geniuses like Euler and then Lagrange and then Hamilton, they each picked up Maupertuis's raw, unpolished idea and just forged it into something precise and powerful. They gave it the mathematical rigor it needed, they generalized it, and they finally reframed it in the modern language of energy. And suddenly, we have a much more powerful kind of physics. This principle surpasses F equals ma in some really important ways, because now this refined principle, it wasn't just some philosophical curiosity anymore. It became a brand new and incredibly powerful way to actually do physics. And in a lot of cases, it turned out to be far, far better than even Newton's famous laws. Okay, but that brings up a really important question. I mean, if we already have Newton's laws, if we have F equals ma, and it works great, why on earth would we need this other seemingly more complicated thing? Well, it really comes down to two completely different ways of looking at the world. Newtonian physics, on one hand, is all about forces and vectors, pushes and pulls that have a specific direction. It can get really complicated with all those arrows. But this new approach, which we call Lagrangian physics, it's totally different. It's based on energies, kinetic and potential. And energies are just numbers. There's scalars. There's no direction to worry about, which, trust me, can make solving problems dramatically simpler. And the power of this Lagrangian approach is just immense. In practice, it's like a magic machine. You just have to write down two things, the kinetic energy and the potential energy of your system. That's it. Then you plug them into this sort of crank, a special equation, and it just spits out the correct equations of motion. It makes handling really complex systems so much easier, and it lets us solve notoriously hard problems like the chaotic motion of a double pendulum with honestly surprising ease.
Okay, one small but important correction. We've been calling it the principle of least action, because that's its famous name. But technically, it's more accurate to call it the principle of stationary action. All that means is that nature finds a path where the action is at a flat point. Think of it like the top of a hill or the bottom of a valley. So it could be a minimum, but it could also be a maximum or something else. For what we're talking about, though, the main idea of optimization is still the key takeaway. And that really brings us to this incredible unified view of the universe. We've come full circle, haven't we? We started with a simple little riddle about the fastest way down a ramp, and we've ended up with this single, incredibly profound principle. It's a rule that describes everything, from light bending in water to pendulum swinging, all the way to planets orbiting a star. It's truly amazing. But you know what? The story doesn't even end there. This idea, the spooky principle of action, it turned out to be absolutely central to the development of quantum mechanics. And even life itself, maybe? It really raises this final, tantalizing question. If nature is always optimizing, if it's always looking for the most efficient path, could this principle be a clue not just to the laws of physics, but to the very emergence of life? Now that is something to think about.